Hello, everyone. My name is Benjamin Asmeni, together with Frederick Damte, and we are going to present on our project Clinical Decision Support for Early Identification of Obesity-Related Complications Risk. Obesity remains a major global health challenge linked to conditions like diabetes and heart diseases. And early identification is crucial because risk factors can still be modified. And in practice, clinicians often miss early signs due to heavy workloads. So a CDSS can help by rapidly integrating patients' data to supply timely, evidence-based clinical decisions. And AI-powered CDSS tools can interpret complex patients' data and deliver steady, reliable recommendations. A study also suggests that machine learning models often predict obesity risk more accurately than traditional methods. Yet many of these models remain difficult to interpret, leaving clinicians unsure on how the system arrived at its recommendations. For our target populations include adults at risk of obesity-related complications, and this population is ideal because risk factors are modifiable and early interventions can significantly improve long-term outcomes. So, in reviewing our work, in reviewing previous works, recent studies shows that machine learning models can improve obesity risk predictions. Hybrid and Ensembles method performs especially well. Visualization tools also helped by making the models easier to interpret. AI often performs better than traditional statistical methods in these areas. Despite these advances, many existing models are not part of real clinical decision support workflows. They also rarely include feedbacks from clinicians. And our project seeks to address this gap by building an explainable and clinician-centered CDSS. Our aim is to build an explainable CDSS that predicts 7 obesity-related risk categories and support clinician or clinical decision making. We use the Kegel obesity risk data set containing over 20,000 samples and 18 features. And the target consists of 7 classes ranging from insufficient weight to type 3 obesity. We validated the data set. We validated that the data set had no missing values and all features were properly structured. So to ensure generalizability, we use stratified k-fold cross-validation so that each fold preserved class balance. My colleague Fred will continue from here.
Thank you very much, Ben. Now, these were the processes we followed. We made sure we ingested data from Kaggle using the JSON token, and then did data exploration to see data set characteristics before we went ahead to pre-process the data. The pre-processing include cleaning the data. We could see that there were no missing values, so we defined features and target. The only problem we realized was that the ID column was not relevant for the prediction, so we dropped that column. We also realized that one of the classes, which was the normal class, was misspelled. So we corrected that spelling to make it normal. And then we went ahead to define the features and target, and then split the data set into the training and then test place in the ratio of 80 to 20%. We didn't include validation because we implemented threefold cross validation in the training phase. The model which was used for our prediction is the orthogonal tabular predictor. And after which we evaluated our model on accuracy, on AUC, F1, and confusion metrics. Then we also implemented explainable AIs, sharp local XI explainable AI, and then contrastive explainable AI was used for explanation after the testing phase and also within the clinician in the loop interface to enhance clinical understanding. Now, these are the processes we followed earlier. So a little bit about Toglon. A Toglon is a model which has it's a machine learning framework which has multiple models. Mainly they are random forest, XGBoost, Light GBM CATs, GBM neural networks, and they are derivatives. With our project in particular, the derivatives in total, to including the ensembles, we have 65 models. Now, at the end of the training and testing, these were the top performing models. Large GBM BAC 1 was the best performing with test accuracy of 0.904, and you could see the values for the others. But the most important is that all the model, these top 10 models, in addition to most of the other models, are able to distinguish between the 7 classes of obesity very well, which is something good. This is the ROC curve for the top 10 models. And then the confusion metrics and classification reports. Now, this is the sharp to explain our model prediction. When we plotted, we realized that the top 10 predictors for obesity risk complication were the family history of obesity, the weight of the patient, age, height, gender, vegetable consumption, and then high calorie food consumption. So you could see from the plots that especially weight, gender, height, and age are very strong predictors. After which we went on to develop our clinician in the loop interface. And this allows clinicians to give feedback by accepting, rejecting, overriding suggestions, and adding the reason for that. There were also justification, text, and timestamps log for auditability. Now, with the interface, this is the interface. A case index is selected, and then it outputs the case accuracy, the predicted class, and the actual class based on the data set. And once it gives that, you're able to know whether the model accuracy is high enough or is low enough. It also gives additional information like the timestamp and all that. We are also seeing the case, the local explainable AI, which is plotted as something like a waterfall over here. And then you also see a contrastive AI explanation, which is also over here, where you compare the current case prediction to a standard case prediction based on what is selected. This is the interface, the session which allows clinicians to give the feedback. And we had a number of challenges. First, using Autoglon was a bit challenging. We wanted to do a lot of pre-processing ourselves. In fact, we did it, but later realized that Autoglon doesn't accept heavily pre-processed data. Once we do that, it's going to affect our predictions. It sees the normalized and the scaled classes as numbers instead of seeing them as categories, which affects our model prediction. Developing the Streamlit clinician in the lab was also a challenge, and then this is also a 7 multi-class task, which made analysis of it a bit difficult. And time was a very limiting factor, preventing us from doing a very robust modeling. In conclusion, we have developed a good model to predict obesity-related risk, with each of them achieving quite sufficiently good accuracies and then AUCs. Going forward, we want to further develop our model so that it could help to detect in early identification of high-risk patients, and it will also help with more personalized counseling and resource allocation. And finally, it is going to help in population-level prevention strategies. Thank you. These are references. Thank you.